Hello students, happy morning. Class 12 Physics, Unit 7, Wave Optics continuation video. Here in today's class, let me see what is Eigen principle in wave theory, and also let me prove the law of reflection and refraction with the help of the Eigen principle. First, let me see what is Eigen principle. Okay, why we are using the Eigen principle? Eigen principle. That is a principle given by Eigen that was proposed in wave theory. Okay, in order to explain the propagation of wavefront. To explain the propagation of wavefront. Okay, here by using this theory, we can give the shape of the wavefront at any instant of time by knowing the shape of the wavefront at t is equal to 0 second. Okay, here let me see the Eigen principle. See, according to the Eigen principle, each point on a wavefront that behave as a source of secondary wavelets that spreading in all the direction with the speed of the wave. Okay, that are known as secondary wavelet. Then the envelope to all the wavelet give the position and shape of the new wavefront at a time t. Okay, first of all, here I consider a propagation of spherical wavefront. Propagation of spherical wavefront. Okay, we know a spherical wavefront is coming from a source, that is a point source that is placed at a finite distance. Okay, then the wavefront will be a spherical wavefront that is named as AB. The wavefront is AB. Here I consider 3 points P, Q, R. P, Q, R. These are the source for secondary wavelet. Okay, how to draw the secondary wavelet? We know these wavelet are the wavefront that travel with the velocity c. Okay, here I drawn a circle by the length, by the radius, that is ct. Here also. Okay, then after I drawn a tangent on these small circles. This tangent indicate the new wavefront, that is a dash, b dash, or the secondary wavelet. Okay, here the p, q, r that act as a source for this secondary wavelet. Okay, with the velocity that is c. Then next, let me consider a plane wavefront. Propagation of plane wavefront. Here I consider a plane wavefront. So the source is at a infinite distance. The source may be a point source or a line source, but it is at a infinite distance. Here I consider a plane wavefront. On that plane I consider 3 points P, Q, R. Okay, here I drawn a circle having the radius ct. Then the tangent of the circle gives a new wavefront, that is a secondary wavelength. Okay, by using this knowledge, let me prove the law of reflection. Okay, and also let me prove the law of refraction. We know the law of reflection that state the instant ray, the reflected ray, and the normal all lie in a same plane. And the second law, that is angle of incidence is equal to angle of reflection. Okay. Our next topic, that is proof for law of reflection using Eigen principle. So far I consider a reflecting surface. I consider a reflecting surface that is named as X, Y. Here a beam of parallel rays, that is LM, that fall on the reflecting surface. Okay, this is named as LM, that fall on the reflecting surface at the point A and B dash. Okay, then according to the law of reflection, it will reflect. this is a reflected ray. Okay, this is a reflected ray, that is L dash, then this one is M dash. At the point of incident I drawn a normal. Here also I drawn a normal. Okay, this normal is named as N. Here this is named as N dash. Okay, we know the wave front is always perpendicular to the propagation of the wave. Okay, so I consider a wave front that is perpendicular to the instant ray. This is a wave front that is named as AB. Here it is a reflected wave front. This is a reflected wave front, that is B dash A dash. Okay, we know this is angle of incidence, this one is angle of reflection. Okay, see, the angle between the instant wave front and the surface is known as angle of incidence according to the geometry. Okay, and also we can consider the angle between the reflected wave front and the plane surface, that is angle of reflection R. Okay, then let me solve the, or let me prove the law of reflection. We know the law of reflection. Law of reflection, that is we know very well. First law, that is instant ray, reflected ray and the normal all lie in a same plane. Okay, and the second law, that is angle of incidence is equal to angle of reflection. Okay, here we know the first point that we proved, the angle of incidence, angle of the instant ray, the reflected ray and the normal all lie in a same plane. Then the second law we have to prove, that is angle of incidence is equal to angle of reflection. Here I consider the angle I. Angle of incidence is equal to, we know, that is angle NAL. That can be written as, see, angle I is NAL. That can be written as 90 minus NAB. That gives angle BAA dash. Sorry, BAB dash. Okay, that is 90 minus angle NAB. That gives the value, that is BAB dash. This is angle of incidence. Then angle of reflection, that is R. Angle R is equal to, we can write, that is N dash B dash M dash. Angle N dash B dash M dash. That can be written as 90 minus N dash B dash A dash. 90 minus N dash A dash, sorry, N dash B dash A dash. That is equal to angle A dash B dash A. Okay, here we know this angle is 90 degree. Okay, this angle also 90 degree. Then the triangle AB dash and the triangle B dash A dash A are right angle triangle. Right angled triangle. Okay, because the angle B is equal to angle A dash is equal to, that is 90 degree. Here the side AB dash, that is a common for the two triangle. Okay, so we can consider this is a 90 degree. Okay, this also 90 degree. So the side A dash is equal to B dash, that are equal. Okay, so this triangle AB dash and B dash A dash A, that are congruent triangle. Okay, these two triangles are congruent triangle, so we can see this also 90 degree, this also 90 degree. The value a dash and b dash are same. Here this is a common side. Okay, so we can consider angle I is equal to angle R. That is a property of congruent. Okay, by the property of congruent, angle I is equal to angle R. Okay, here the law of reflection is proved. Then let me see the law of refraction by using the Eigen principle. Then our next topic, that is proof for law of refraction using Eigen principle. Okay, for that, first of all I consider a refracting surface that is named as X, Y. Here there is a beam of parallel beam of light that fall on that refracting surface. Okay, here the surface that separate the two medium, here it is a medium 1, here it is a medium 2. This is a rarer medium, this is a denser medium. So at that point I drawn a normal. Here also normal. We know the ray of light travel from rarer to denser medium. Okay, it will bend towards the normal. Then there will be refraction. Okay, here also refraction. It is a angle of instance I. This is angle of refraction R. Here also angle of instance I. Here also angle of refraction R. Here it is the instant ray, that is L. Here it is M. This is L dash. This is M dash. Okay, here the normal is named as N. Here it is named as N dash. Okay, this is N dash. Then after I drawn a instant wavefront in first medium. The wavefront is perpendicular to the instant ray. Okay, this is that wavefront. That is named as A, B. Then I draw a refracted wavefront that is perpendicular to the refracted beam. Okay, this is A dash, this one is B dash. Okay, here we know the velocity of the light in the first medium, that is V1, in second medium, that is V2. Here it is a rarer medium, it is a denser medium, so the velocity of light in rarer medium is greater than velocity of light in denser medium. Okay, here the time taken by the wavefront from B to B dash is equal to the time taken by the wavefront from A to A dash. Okay, here this is a rarer medium, here this is a denser medium, so I consider the velocity V1. V1 is equal, that is the displacement by time. Here the displacement is B to B dash, B dash, and the time is T. Then next V2, it is in denser medium. The distance is A dash, A to A dash, the time is T. I already mentioned the time taken to cross a distance B to B dash is equal to A to A dash. Okay, so we can equate this one as T is equal to B dash by V1. This one as T is equal to A dash by V2. Okay, equate these two, then we get B dash by V1 is equal to A dash by V2. After solving this, then we get B dash by A dash is equal to V1 by V2. Okay, then next let me prove the law of refraction. Law of refraction, that we know instant ray, that is LA, refracted ray, that is A L dash, and the normal all lie in a same plane. That is the first law. Then second law, that is we know, that is a Snell's law. Okay, Snell's law, we know ratio of sine of angle of incidence to the ratio of sine of angle of refraction is equal to ratio of referent x of the first medium to the referent x of the second medium. Sin I by sin r is equal to n2 by n1. Sin I by sin r is equal to n2 by n1. It is the second law of refraction. Okay, here we have to prove the second law. This is already proved. We know incident ray, the refracted ray and the normal all lie in a same plane. Okay, then the second law, that is sin I by sin r is equal to n2 by n1. First of all, we need to find the value of sin I. So we need the value of r, I and r. The second law, that is sin I by sin r is equal to n2 by n1. Okay, we need to find the value of I. Angle I is equal to, that is angle NAL, that is equal to 90 minus NAB. NAB, that is equal to angle BAB dash. Okay, I already told the angle between the incident wavefront and the surface is known as angle of incidence, and the angle between the refracted wavefront and the surface is known as angle of refraction. This also we can indicate like this. Here it is r. Okay, then this is a 90 minus r. Okay, this is r. See, this value is 90 minus r. Okay, here this is 90 degree, so we can say this one as r. Here also it is 90 degree, this is 90 minus I. Okay, here this is 90 degree, so the summation of triangle will be 180 degree. Okay, we can write 180 is equal to, this is x, then 180 plus x plus 90 plus 90 minus I is equal to 180 degree. Then we get that the x value became I. Okay, or we can simply say it as the angle between the incident wavefront and the surface is I. The angle between the refracted wavefront and the surface is r. Okay, then the angle of refraction r is equal to, that is here n dash b dash m dash, n dash b dash m dash. Okay, that is equal to, here this is overall is 90 degree, then we can write 90 minus n dash b dash a dash, that is equal to angle a dash b dash a. Okay, here the two right angle triangles are there, that are a b b dash. One more one is a dash b dash. Okay, two right angle triangles, angled triangles, that are triangle a b b dash and the triangle a dash b dash. Okay, here I consider the sin I. Sin I is equal to, see, sin I is equal to opposite side by hypotenuse, that is b b dash by a b dash, b b dash by a b dash, and sin r is equal to, see, opposite side, that is a dash by hypotenuse, that is a b dash. Okay, then we know that is sin I by sin r. Sin r is equal to b dash by a b dash by a dash by a b dash. Cancelling this, then we get b dash by a dash. We know b dash by a dash, that is equal to p1 by v2. Okay, so we can write sin I by sin r is equal to p1 by v2. Okay, here I can write that is c, here it is c. Okay, we know the velocity of light in vacuum to the velocity of light in medium is refractive index of the medium, n1. Okay, here it is. See a little mistake. See, we know sin I by sin r is equal to, that is, we get v1 by v2. Okay, here we can write this one as 1 by v2 by 1 by v1. Okay, here I am multiplying c on both numerator and denominator. Here we get velocity of light in vacuum to the velocity of light in medium, that is known as refractive index of the medium, n2. Here it is refractive index of the medium, n1. Okay, then we get sin I by sin r is equal to n2 by n1. The law of refraction, that means Snell's law, is proved. Okay, here we can write this one in a product form, that is n1 sin I is equal to n2 sin r. Okay, here in this case we are sending the light waves from rarer to denser medium. Okay, we can allow the light from denser to rarer medium. At that instant also we get a same result. Okay, here from this we get the knowledge, that is the velocity of the velocity of the light is inversely proportional to the refractive index of the medium. That means the refractive index increases, then the velocity of light decreases. Okay, that's why the velocity of light in denser medium is greater, velocity of light in rarer medium is greater than in denser medium. Okay, and also we get the knowledge, that is velocity is directly proportional to wavelength. That means the wavelength increases, velocity increases. This is from the expression, that is we know velocity of the light, that is c, is equal to nu lambda. Here nu is a frequency and lambda is a wavelength. Okay, here c is proportional to lambda. That means in all the medium the frequency of the light is constant. Frequency is constant in all the medium. The only change is wavelength. So the velocity of light is changing in all the medium. Okay, we know very well, if a light travel from rarer to denser medium, in rarer medium it having the velocity c. Okay, at that instant it having the wavelength lambda r, the frequency is nu. Then after that refraction take place, then the velocity became v. At that instant the frequency in that medium will be nu only. There is only changing in wavelength. Okay, only change in wavelength. Always the velocity of light in a rarer medium is greater than velocity of light in a denser medium. Okay, thank you.